When he was 70 years old, Robert Adams of New Zealand designed a very effective motor generator. He was told to destroy his device or he would be killed. Robert decided that at his age he had very little to lose, and so he published his design. His motor overcomes the Lenz's law drag effect, and through clever engineering achieves a power output which is 8 times greater than the input power. Although it does not look as if it is, his design is actually a permanent magnet motor. The diagram of his motor, which is supposed to show how it works, is this. This gives the impression that the rotation of the rotor carrying the permanent magnets is driven by electrical pulses like John Bedini's famous motor. It isn't. This is a permanent magnet motor, and the rotation of the rotor is caused primarily by the magnets in the rotor being attracted to the solid iron cores of the two drive electromagnets shown in the diagram. The electromagnets confuse people, as they don't realize that the level of power applied to them is so low that it only just cancels the backward drag of the magnets as soon as they pass the electromagnet cores. That happens 4 times per revolution, and the power is only switched on when the rotor magnet is exactly aligned with the electromagnet, and then only briefly. These two electromagnets, along with their very carefully timed electric pulses, are the entire drive for the generator. The timing of the drive coil pulses is arranged by an optical timing disc of this type. The timing disc is mounted on the side of the rotor, and the sensor is operated by slots cut in the rim of the actual timing disc. Let's concentrate on the drive for the moment. After much experimentation, Robert found that the most efficient arrangement is when the cores of the drive electromagnets have half the cross-sectional area of the rotor magnets. So if the rotor magnets have a circular cross-section, then their diameter would be twice that of the drive electromagnet's diameter. Robert also found that the best gap between the rotor magnets and the drive electromagnets is about half an inch, which is 12 millimeters. A further tweak to the drive system is the fact that the drive electromagnets are fed a continuous stream of electric pulses. Now, when a coil is powered up and then the current switched off, the coil generates a reverse voltage pulse, sometimes called a back EMF pulse, a term which annoys some electronic purists no end. In Robert's motor generator, those back EMF pulses are used twice. First, as the coils are energized in order to oppose the attraction between the rotor magnets and the electromagnet cores, the back EMF, being in the opposite direction, causes the reverse effect, increasing the attraction to the next approaching rotor magnet. Second, Robert rectifies the back EMF pulses and feeds them back to the drive battery, and that recovers 95% of the current needed to make the generator work. Now we come to the power generating system, and one person who has replicated this device has an excess power output of 33 kilowatts, and that powers his house and his business. The power generation is through 4 additional electromagnets which act as pickup coils. This is Robert's drawing of his arrangement. You will notice a number of things here. The 4 generator coils are mounted physically on a disc or a ring, while the 2 drive coils are separately mounted on their own mounts. This means that the gap between the generator coils and the drive coils can be adjusted while the motor is running. Also, you'll notice that the width of the core of the collector or generator coils is very much greater than the width of the core of the so-called drive coils. The generator coils in his drawing are very nearly square. Next, you need to notice the proportions of the rotor magnets. They're very much longer than they are wide, separating the outer north poles from the inner south poles. However, a point which seems to escape most people is the fact that a critical part of the design is the technique of cutting off the output power at the appropriate moment. Cutting off the output power sounds all wrong to most people, and yet it's a very important thing to do. The reason is the same as for the drive coils. If you don't cut off the electrical connection, then the attraction between the solid iron cores of the generator coils and the rotor magnets tries to pull the rotor magnets back towards the fixed generator coil cores, an effect which is called drag. But if the output current generated in the coils by the passing magnets is cut off at just the right instant, then the back EMF generated by that cutoff causes a magnetic field in the generator coils which boosts the rotor on its way instead of dragging it backwards. Robert also rectifies that back EMF pulse and feeds it back to the drive battery. So far, this is a highly efficient system. Robert's diagram doesn't show when the generator coils are best switched on or off. A builder with the forum ID of Memiara found optimum switching would switch on at 40 degrees and switch off at 44.7 degrees. That tiny 2.7 degree part of the rotor turn gave him an input of 27.6 watts and an output of 33.78 kilowatts, which is a coefficient of performance of 1223, or 122,300%, which is spectacular. It's suggested that a good length for the generator coils is shown when your particular rotor magnets just start to lift one end of a 32mm long paperclip off the table, like this diagram shows you, and that indicates the coil width, and it's generally a good idea to have the width of the coil 1.5 times the coil length. Robert takes his design further by using short pulses of current. This is something which is done after the rotor operation has been optimized using continuous battery power. That is, after moving the generator coils on their disk to find the best performance position and controlling the length of the pulse with the timing disc. Robert preferred to use mechanical contacts on a rotating disc to create the on and off current pulses. The disc itself is very small, but shown large here so you can see it. There is a fixed position brush and a variable position brush which slides in a slot, and the position of the brush along the metallic contacts on the disc alter the percentage of time that the current can flow. Seen from the side, you can see the fixed position brush and the variable position brush, whose position can be fixed by bolts going through a slot in the mounting here. The objective is to adjust the variable position brush to get the power connected to the motor generator for only about 25% of the time. The timing disc shown above is attached to the rotor shaft, and so no additional power is needed to achieve the switching, and the switching allows current flow in both directions, which is convenient. And connected this way, with the plus going through the switching through the drive coils, and you need to pay attention to the direction that the coils are wound to make it work properly, and then it comes back and you have a diode and a capacitor, and that feeds the pulse circuitry back to the battery to recharge it. The overall arrangement of the whole circuit is like this. You have the long magnets on the rotor disc, the 4 generator coils and the 2 drive coils, and this is the connecting wiring. The output from the drive coils is of course alternating current. Robert Adams advises the following. 1. Use only pure iron for the cores of the drive and generator coils. 2. Wind the generator coils with a resistance in the range of 10 to 20 ohms for a small model. 3. Use a voltage between 12 volts and 36 volts for a small model. 4. For a small machine, make the contactor star disc, which switches the power on and off, a maximum of 1 inch in diameter. 5. Keep the wiring short and use a low resistance wiring. In other words, the wire diameter needs to be reasonably thick. 6. For a small machine, use a fuse of 500 milliamps to 1 amp. 7. Install a switch for convenience and safety. 8. Use small bearings. Do not use seal bearings due to their grease drag. That is, seal bearings are packed with heavy-duty grease. Now it is possible to overcome that by spinning the central part of the bearing using a power drill. After a while, that frees the drag of the grease, and you get a sealed bearing which does have lubrication and doesn't have great drag. 9. Use only silver contacts for the pulse switching. 10. If using powerful magnets, know that vibration will become a problem. 11. The air gap is not critical, but reducing it increases both torque and input power in proportion. 12. For higher voltage and lower current, connect the generator coils in series. 13. If the drive coil windings are low resistance and the input voltage is high, then it's advisable to use a transistor to eliminate sparking. 14. Tuning the points is vitally important unless you're using transistor switching. 15. Use ferrite magnets for all input voltages below 120 volts. 16. If constructing a large model involving large superpower magnets, then greater power is needed to drive the machine. The greater the torque, the greater the vibration, the greater the copper content, and so on. Please also remember that any wiring you use needs to be able to carry the current without overheating. Here are some continuous current figures for popular wire sizes, and you can see the way that the current that the wire can conveniently carry drops rapidly as the wire size gets smaller. The diameter of the wire gets smaller. If you want them, these notes are available at www.freeenergyinfo.com/adams.pdf.